Hi, everyone, and welcome to this talk about distributed worker system. My name is Neil Orman, and I'm a backend engineer at Wix. I've been developing software for the past 8 years. I was previously a full stack team leader at a startup doing computer vision and deep learning algorithms called DID. I build systems that scale for a living. My true passion is innovation, tech, and software, and I really love learning anything new. In this talk, I'll present the problem of computing long calculations as part of APIs. I'll tell you all about the solution I found for it, how to make it scale, and how to monitor it. Let's talk about the problem that we're going to solve. I'll start with a small analogy, which I'm sure you could all relate to. Think for a second about all the things you have to do this week. Yeah, I know it's a lot of stuff. We are busy people. Let's talk a little bit about what you have to do this week. So maybe you got to cook, you need to walk your dog, you want to work out, maybe you got some laundry to do, clean the house, and work. So you're busy, but what can you do about it? Well, okay, you have to do your own work and exercise. Nobody can do that for you. But what about the rest of your tasks? Get workers to do your task. You don't have to cook. Some people order lunch from Walt. You could hire a cleaner to do the laundry and clean the house. Some people get a dog walker to walk their dog. Where am I going with this? I say APIs are like people. They're busy. Think of them like people. They too have a lot of work to do. Here are some examples to show for it. So they got to create, update, and delete entities. They gotta read and write from the database. They gotta do authorization and authentication of users. They gotta call third-party APIs, and they gotta compute long, complicated stuff like deep learning algorithms or some complicated long-running tasks. As I said, I worked at a startup that developed a computer vision deep learning algorithm for 2 years. When the algorithm was finally ready, it took 10 minutes to get the output of it. A very naive solution would be to run the computations as part of the API request. Don't even try that. First of all, you'll get a connection timeout from the client, and second, no user will wait that long. As I've said, we're busy people, and we've got no time to sit and wait for the server to compute for 10 minutes. Hell, I won't wait a second. That was 3 seconds of silence, but it felt like forever, right? So Google recommends aim for a response time of less than 200 millis. Anything over 500 millis is an issue. API's got to be fast. So what's the solution? How could we return a response quickly and still compute long-running calculations? I was required to choose the architecture, the language, and the infrastructure. So I found the following solution for the task of long calculations. Get workers to do your tasks. Let's see how we would solve this in the human case. So this is you, the busy person that creates tasks according to the task you have to get done. This is your assistant. You hired him to write down all the messages that you get your to-do list. These are your workers that you hired, the dog walker, the cook, the cleaner. They take the tasks from the assistant and get them done. And this is your logbook where you keep track of all the things that you got done this week. Cute story, but how does it really work for a software system? Okay, you guessed it. You're the server. You get the API calls and you gotta respond quickly. Your assistant is really a message broker. It's a first in, first out data structure capable of managing multiple message queues. Distributed workers, they could run in different processes or instances and be scaled according to the workload. They listen to the message broker and perform the task one by one. And the storage, this is the back end. In which the results are saved at. Some kind of a database, like a key value store where the key is the task ID and the value is the task result or the task status if it hasn't finished yet. Okay, we have the system design, but which technical stack should we use to implement the solution? After doing some online research, I came to the conclusion that Python is going to be our backend language and Celery should be the tool used to solve the problem of running long algorithm asynchronously. But I've listened to every Celery talk on YouTube and I haven't managed to understand what exactly is Celery and how does it work. So Celery is an open source, asynchronous, distributed task queue. Open source means it can be used for free, and we can see the source code and contribute. Asynchronous means it happens offline, not in the same process that triggered the code. Distributed means it's running on multiple threads or machines or instances, which is exactly what I needed because the algorithm required a GPU to run and could only compute one task at a time. And task queue, we'll dive into that for a second. A task queue is a mechanism to distribute workers' work across threads or machines. Celery's task queue is written in Python, but the protocol can be implemented in any language. This is the code for creating the Celery app in Python. But what exactly do I mean when I say a task? A task is the queue's input. It's a unit of work, which is really just a Python method with parameters. You annotate the task as shown in the snippet. This task has a name, make coffee, and it gets 4 parameters. Once the worker finished computing the task, which means running the code annotated as Celery's app task, the return value is automatically stored in Celery's backend. You can also provide the task with the configurations such as time limit, rate limit, which queue the task should go to, and even set the task priority. You could also set the task to be grouped together into workflows, one task dependent on another or computed in parallel to another. You can set handlers for what happens when a task fails or succeeds. So we now understand what a task is, but what exactly is a Celery worker? A worker is essentially a process that monitors the queue for new work to perform. So once you have a task in the queue, nothing happens. But if you also have workers listening to that queue, one of them will fetch the task from the queue and compute it. Starting a Celery worker is easy, as you can see in the snippet. Of course, you could add a lot of parameters to it, like log level, number of threads, worker's name. Workers can even do scheduled tasks. So now we know what a task is and what a worker is, but how does the task get to the worker? The API is responsible for producing tasks. In the code where you handle the API request, instead of just calling the method makeCoffee, you call makeCoffee.applyAsync with the right parameters. This would behind the scenes put a message in the message broker saying the task needs to be done with its parameters. Then you can return 200 OK to the client that doesn't have to wait for the task to finish and can be notified once the task is done by email or any other way you choose. Cool. We now know what the API does and what the worker does, what the task is, and what the task queue is. Let's take a look at the technical stack of it. Remember this slide from before? So the API is really Flask, which is a very lean Python server framework. The message broker, the best practice for this one is to use RabbitMQ, which is an open source from 2007. The distributed workers are actually Celery workers, and the best practice for storage database is Redis, a key value store which keeps the task results. Amazing, but now you're probably thinking, okay, we have workers to do our tasks, but it still takes 10 minutes. How would we know when the task is ready? At first, we had the Flask API pull Redis every 30 seconds to check the status by task ID. Is it ready yet? Is it ready yet? But that pretty quickly caused Redis thread problems. Keep in mind that Celery task results have a default time to live of Redis for 1 day, after which the results are deleted. Have you got another idea other than polling Redis? We could use webhooks. Have the task itself call the webhook to notify it completed successfully and write the results to a relational database so it's more organized and won't store large amounts of data on Redis, which gets filled up pretty quickly. Okay, cool. And by the way, where are all those components running? If you just want to try it out, the solution, you could run it all on your laptop, install Python, Celery, Flask, Redis, and RabbitMQ, and run the Flask API, Celery worker, RabbitMQ, and Redis. But that's a really bad practice. You don't want every developer on your team to install all of that. We can do better than this. A better solution would be to run each of them inside a Docker container. Redis and RabbitMQ have a ready image, so it's easy to run inside a Docker container. You need to write a Docker file for running the Flask and for running the Celery workers. You should probably have a Docker Compose file to run the whole setup, but we can also do better than this. An even better solution would be to run all of them in a Kubernetes pod, but we could also do better than this. We could run the whole setup in the cloud. You could use Azure, for example, or GCP or AWS. Your workers could run on multiple instances of different types according to which tasks they perform. For example, a deep learning algorithm needs a GPU expensive instance, whereas a task of calling third-party APIs could be done by a regular CPU cheap instance. You can even have instances in multiple clouds reading the task from the RabbitMQ. If you're running on Azure, use AKS. If you're running on AWS, use EKS, or in Google Cloud, use GKE. Awesome. But in this image, we have just 3 workers. How do I control the number of Celery workers dynamically according to the workload? Yep, we need to scale it. We know the workload changes. Daytime, a lot of traffic. Nighttime, less. Weekdays, more traffic. Weekends, less. Maybe on Black Friday, we have sales, and then there's a crazy traffic. So what can we do to enable auto-scaling, to enable scaling? So the very naive solution to scaling a system is just to manually monitor the length of the queue. And once you see there are a lot of tasks, you manually add instances using your favorite cloud provider with your bare hands. It's fast to implement, it actually takes no time to implement, but it's hard work to keep up with the changing load, and pretty quickly you'll forget you scaled up and pay the fine for leaving multiple instances that are very expensive running for no reason. We need something a little more sophisticated. We need an autoscaler. Remember this slide from before? Let's add an autoscaler to it. That would scale according to the number of tasks in the queue. But how? What do we put in this magic box? We need the scaling to be flexible and dynamic because we don't want to pay for workers' instances which we don't need and we don't use. So we need to monitor the length of the queue and add and remove instances according to it. What should we put in this magic box then? It's simple. A Python script that runs every 30 seconds or so and checks how many tasks we have in the queue and sends the API request to the cloud to change the number of pods in the cluster. There are a bunch of pitfalls to this, believe me, but talking about autoscaling can fill an hour talk just by itself. So now we have this simple autoscaler that scales our cluster. So we have as many workers as we need, but it seems that it adds more and more workers. How do we not lose control? Well, that's what they invented monitoring for. How do we monitor Celery? Celery has a monitoring tool called Celery Flower, which allows you to see how many workers you currently have, how many tasks each worker has completed, etc. You can also see the results of the tasks that finished and exceptions of tasks that failed. We also can use RabbitMQ by using RabbitMQ admin UI. It allows you to see how many tasks are waiting in each queue, and you can pop them out of the queue to see their content before they go to a worker. Let's do a quick recap. So we've seen that any API should strive to return a response in less than 200 milliseconds. If your API takes longer, you should consider outsourcing to asynchronous computations. We've seen a solution for the problem by distributing the work among multiple workers that take tasks from the queue. We've seen you can autoscale the amount of workers according to the length of the queue. And we've seen you can monitor it using Celery Flower and RabbitMQ admin. Our workers are doing heavy lifting and long calculations for us so that our APIs could be super fast. So remember that for every 2 minutes of glamour, there are 8 hours of hard work. And it's as true for APIs as it is for humans. We need heavy backend calculations to happen asynchronously in order for our APIs to be fast. Our API respond quickly, but behind the scenes, our workers are doing all the heavy lifting. And if you're too busy, Remember, you can always get workers to do your tasks. I know it's complicated. You can read more about it in my Medium blog that I published, Serving Deep Learning Algorithms as a Service. Thanks for listening, and feel free contacting me.